So in this lesson, our goal is to learn combustion analysis. We want to learn what is combustion analysis, how do we solve combustion analysis math problems, and where we're going to start is, well, why? Why are we doing combustion analysis? Well, the thing to understand about combustion analysis is it's just a method for determining the empirical formula of a compound. And we've already done this quite a bit. I mean, if you think about it for a second, we it depends on which lab we do, but sometimes we do, finding the empirical formula of silver oxide, where we decompose it into its elements, right? And if we know what the masses of silver and the masses of oxygen after you've separated those elements, those would have been the same masses in the original compound, and we can convert them to moles and figure out the empirical formula. Sometimes we go the other way. We start with pure magnesium and oxygen, and we figure out the empirical formula of magnesium oxide by figuring out how much mass of each individual element composed the final compound in the end. But you'll notice with all these methods, the key thing is you have to, at some point, either the beginning or the end of the reaction, have the elements in their pure form. Well, if we were to try the same thing with some sort of hydrocarbon, the trick doesn't work, right? So a hydrocarbon is just something that contains hydrogen and carbon. So like, say for instance, methane gas is an example of a hydrocarbon. Or let's see, we could have ethane gas, so C2H6, right? It doesn't matter how many hydrogens or carbons there are, those are hydrocarbons. Hydrocarbons can also include other elements, like you might come across something that has carbon, hydrogen, and oxygen in it in various ratios, or maybe even carbon, hydrogen, and nitrogen, or carbon, hydrogen, and sulfur. But in any case, all of these are covalent compounds. And the problem with covalent compounds is if you were to do the same thing that we did with the silver oxide or the magnesium, you were to just heat those things, right? Remember, the triangle means heat. If you were to do that with these hydrocarbons, you don't get carbon and hydrogen, or if you have oxygen, you don't get the elements split out. That just doesn't work. And you know why? Because if you take something like, say, for instance, gasoline, right? Octane, 18, is that right? Anyway, but the point is, if you take gasoline and you heat it, it doesn't split into its elements. It does a combustion reaction. And so combustion reactions don't give you the elements in their elemental form. Like, think for instance down here, I think this is ethanol. Well, if we burn ethanol, what's going to happen is we're going to get CO2 and water. Now remember, our goal was to get carbon and hydrogen and oxygen separated from each other, but that's not going to happen. We're going to get CO2 and water. And so in combustion analysis, we're going to do the same thing we've always done, which is somehow we're going to take the amounts, the grams of CO2 and the grams of water, and get out the masses of our individual elements. So that's the main goal here. So it's a little bit trickier of a problem-solving method than we've been doing, but not too bad. But that's the main idea. So how do we measure? Ooh, let's shrink me down a little bit because I'm taking up too much of the screen. So how do we measure the composition of a compound? Well, if we're doing combustion analysis and we're getting CO2 and water, then we're going to get masses of actual CO2 and water. And this is sort of how the piece of equipment works. You burn the sample, and these pieces of equipment tend to be a little bit expensive, so it's not like something we're going to see in a high school lab. But in any case, essentially they have a water absorber and a CO2 absorber. And these containers, of course, when they absorb the water, they gain mass, and you can see how many grams of water you picked up. But the amount of carbon, the moles of carbon which we're going to need, is going to be determined from the mass of CO2. I think that makes sense, right? And the amount of hydrogen in there, or the moles of hydrogen, is going to be determined from the mass of water. That makes sense. Water has H in it, right? We're just going to have to do a little mathematical manipulation. But the hardest part of all of it is if you do have any oxygen in there, if you have any nitrogen or sulfur, that third element, whatever it is, can't be figured out from the mass of these two gases. you actually have to do a little bit of a mathematical manipulation, which I'll show you in a minute. So if that doesn't make sense, it shouldn't, because I'll show you that in just a second. All right, so that's our general strategies. Pull the carbon out of the CO2 amount, pull the hydrogen moles out of the water amount, and then the oxygen. We'll show you there at the end how to do that. But that's our goal. Our goal is not to figure anything else out about this reaction. Our goal is simply to figure out the empirical formula of whatever hydrocarbon we're dealing with. Now in the example I'm going to show you, I actually don't think it's ethanol, but in any case, any hydrocarbon. Okay, so here's the example. You know what? We're going to get rid of me. Isopropyl alcohol is composed of carbon, hydrogen, and oxygen. So this is our hydrocarbon that we're trying to figure out the empirical formula for. Combustion of 0.255 grams of that substance. So this is the original actual substance, and that's going to turn out to be an important number at the end. It's not so important right now, but it's going to be an important number at the end. Once you combust it, it produces 0.561 grams of CO2 and 0.306 grams of water. And our job is to find the empirical formula. So remember, which element are we going to pull out of the amount of CO2? Well, that's going to be the carbon, right? And we're going to use this value to figure out the hydrogen. And then we'll figure out the oxygen at the end. Okay, so let's take this. Let's do the carbon first. I'm going to take 0.561 grams. I'm going to pull it down here, and I'm going to use it to figure out how much carbon there is. Now, first step naturally in chemistry almost always is to convert grams to moles. So if I do that, if I take my 0.561 grams and I convert it to moles, the molar mass is 44.01 grams per mole, and that gives me the moles of CO2. Well, since there's only one carbon in each CO2 molecule, that means it also gives me the moles of carbon, because the mole ratio, because there's only one carbon in it, is 1 mole of CO2 to 1 mole of carbon. So if I stop here and I calculate the answer, that'll tell me how many moles of carbon I have. So we're pretty far along here, because you'll remember that if we know the formula for the compound, let's say CHO, these values are all in moles. So this value will go right there, in there for the X. Okay, let's do hydrogen. Well, for hydrogen, we're going to need the grams of water. So if I pull that down at 0.306 grams, I'm going to convert it to moles. But you'll notice there's a difference in our math here. And once I convert the grams to moles, I'll have moles of water. And when I go to do my mole ratio to convert it into pure hydrogen, there are 2 hydrogens in each water molecule. So 1 mole of water has 2 moles of hydrogen in it. And then when I do my math, I get 0.03396. So we're doing pretty good. Now we know what Y is up here. We have the mole amounts of 2 of them, and we could just do that simplification if we knew oxygen as well. All right, so things are going pretty well. Now this gets to oxygen, and oxygen is the trickiest part. People have this feeling that in some way they should be able to pull the oxygen amount out of the CO2 and the water, but I want to show you why you can't. And this is the most important thing to get in your notes, because oxygen, the last element, could be nitrogen, could be sulfur. The last element is the one that throws people off the most. Well, remember, we're doing a combustion reaction. We're making the CO2 and we're making the water. And yes, all the carbon in CO2 came from that. And all the hydrogen and water came from that. But the oxygen in these 2 molecules didn't just come from our isopropyl alcohol, right? That's what that is. There was also some combusting of oxygen. So some of these oxygens actually did not come from our compound. So if we were to figure out the mole amount for Z, including some stuff from oxygen gas, that would be more oxygen than we actually have. So we can't do that. You cannot figure out the amount of oxygen by trying to use the gram amounts of CO2 or water. That's the most important thing to get in your notes. When you're going to get that third element, oxygen or nitrogen or sulfur, don't look at the amount of CO2 and water. Because I've seen people do all sorts of crazy stuff, like they add up the gram amount of CO2 and water and they try to do something similar to what we've done before, but you can't do that. But there is one thing we could do. Right? Remember, this value up here, which we've been ignoring so far, is the amount that the original compound weighed, the original total mass of that compound was 0.255 grams. Well, so to figure it out, if the total mass of the compound was 0.255 grams, if we knew the grams of carbon that had been in it and the grams of hydrogen, well, if we subtract those out, whatever's left has got to be that third element. It's got to be oxygen. So that's how we're going to tackle it, is we know the mass of the total compound has got to be comprised of its elements that are in it, carbon, hydrogen, and oxygen. And it would be pretty easy for us to figure out the mass of carbon in it and the mass of hydrogen in it because we already know their mole amounts. So all we've got to do is take the mole amounts of each one of these, convert them to grams, put them in here, and subtract them from the mass of the total compound. So let's do that. So there's my mole amount. I've converted it to grams, and 0.15 grams out of 0.255 was carbon. More than half of the mass of the compound was carbon. Pretty cool. If I do the same thing for hydrogen, convert it to grams, you can see it's a pretty small amount. I do want to point something out. So this is the second big thing that I want you to get in your notes. A lot of people are sitting here wondering, why did we not use 2.02? Isn't hydrogen H2? And the answer is no, hydrogen is not H2. If in the reaction up here, hydrogen had been elemental hydrogen, as in diatomic hydrogen, sure, we would have used that. But remember, this hydrogen is the amount of hydrogen in that compound. It's not elemental hydrogen. It's just hydrogen. That's a difficult thing to remember there because we get so used to doing the diatomic elements, right? But it was never an element. It was always in a compound. Okay, so we're doing pretty good. We've got these two amounts. We're going to plug them back up in here and do that subtraction. So there they go. There's the 0.15, there's the 0.03. When I subtract it, I get 0.0676 grams of oxygen. And now that we have the amount of oxygen, we can come down here and we can convert it to moles, and we will know what Z is up here, right? So let's do that. Okay, so there it is. Same with oxygen. You might think, oh, it's diatomic. But no, in the compound up here, it was not a diatomic element. It was just an element, right? So I don't use the diatomic molar mass, and I get 0.004225. There we go. We know X, we know Y, and we know Z. We can plug those numbers in. There they go. Right there, right there, right there. And you know what we do from this point is just like what we've always done before. We divide by the smallest one to get whole number ratios. Smallest one looks to me like oxygen. So when I divide them all by 0.00424, that's what I get. And we got to make a judgment call. Is this close enough to call it good? I think yeah. You know that if it was 3.25, we'd multiply everything times 4, right? If it was 2.99, fine. 3.01, fine. This one's starting to get a little bit far, but it's not jumping out at me like it's not 8.33 where I'd multiply everything times 3, right? So I think that's it. And it turns out, yes, that is the empirical formula of isopropyl alcohol because it has 1, 2, 3. This is its actual structure, right? 1, 2, 3 carbons, right? Should have 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. It does, and it should have 1 oxygen. So its empirical formula does appear to match its structural formula. And there we go. That's how you figure out. That's how you use combustion analysis to solve empirical formula problems for organic or covalent compounds, things that are not ionic, things that don't burn into their elements so easily. But I want to go back to here and point this important thing out, which is the strategy is find out how many grams of carbon are in the CO2, find out how many grams of hydrogen are in the water, find out how many grams of oxygen there were by subtracting from the mass of the original compound.